Hello, everyone. Welcome to this session of ML in Finance. My name is Aslı, and I work as an applied ML engineer at Algorithmia. And today I'm happy to volunteer for the MLOps community and introduce one of our brilliant speakers. Before we start, I'd like to remind you that if you have a question, feel free to post it in the chat during the talk. And when the presentation ends, I'll be asking those questions to our speaker. And now in this session, we have Olga Tsubiks from RBC, the Royal Bank of Canada. Olga is a senior manager strategic analytics at RBC, where she applies machine learning and automation for capacity planning and optimization. She's been working in the field of data science for over 10 years. And Olga brings data to life through machine learning, analytics, and visualization. And outside of her work at RBC, she's worked directly with global organizations such as the UN Environment, World Conservation Monitoring Center, World Resources Institute, as well as prominent Canadian nonprofits such as War Child Canada and Rainbow Railroad on various data science and analytics challenges. So she has a vast experience, as you can see. So please join me in welcoming Olga, and now I'll pass the microphone to her. Welcome.
Thank you. Thank you so much for this kind introduction. Hello and welcome everyone to the session, and thank you for joining. Really happy to be sharing the lessons learned and the experience in AI augmentation today. So I'm gonna skip through the intro slide. The agenda for today is to really talk about the AI augmentation, what it takes to put it into production, what are some of the things to be aware and think about early on to avoid common pitfalls, and also what are some of the parts of the process that aren't necessarily frequently talked about or covered in the literature. So that's the agenda for today, and I'm sure many of you have seen it because it's been published, but I want to also focus on what I hope you will take away from the session today. So one of the things to note right away is that AI augmentation isn't talked about a lot. You hear a lot of other topics, and I will talk about them, but it's important to know that it is a field where a lot of work is happening right now. According to research, about 25% of all investment goes into this today. So it isn't a small field, but it is an emergent field. And it's been around for a while, for a long time, but as we progress with machine learning techniques, and as we progress with what is possible with data science overall, it becomes emerging again and again. And we'll talk about some of the use cases from the past and also from the present. So at the very minimum, what I hope you will walk away from today's session is an idea of how you could apply AI augmentation in your work, or at least an understanding on how to find that use case for your specific area and for your environment where you could apply AI augmentation. So this is the three reasons that I hope you'll stick around for the talk. So as I mentioned, going back to the why this area is important, you hear a lot about robotics, computer vision, and other hot fields in AI. And those are great. It's always important to keep track of what's going on, what is new in the field. But it's also important to know what is the work that's happening today and have the skills applied to that. So according to Gartner and the research that they've been conducting through surveys, they've asked decision makers on where are you spending your AI budget? What are the money, all of your AI budget, what is it going towards? And according to their finding, 21% of all the fund goes into the decision augmentation, or augmented intelligence as it's sometimes called. And that is paired with process automation and some other use cases. So AI augmentation isn't necessarily a niche topic as it's sometimes perceived, because it's not covered extensively on the news every day. So just wanted to mention that to make sure we have common understanding of where the field is today. Now, since I know many of you are at different parts of your career journey and at the different levels of familiarity with AI augmentation, wanted to start with defining what is it all about. Here are the definitions that you commonly hear, but in a nutshell, at the very core of it is that idea that with AI augmentation helps to enhance the human and helps them make decisions and making us all smarter and better, rather than other approaches such as automation, where AI is typically used to free our time for other tasks that might be less complex. So AI would be better at it, or might be mundane and not interesting for humans to do. So if you are interested, if you see yourself as someone who is interested in helping people making decisions rather than less work with people, if you want to work with people, this is definitely an area to pay attention to and to look into and learn more about. So what is AI augmentation and what are some of the use cases? Because everyone's background today is different, I want to actually focus on an example outside of a field of finance. So this one is an example from radiology and healthcare, which is a CAD mammogram. So this use case for AI augmentation has been around for a long time. And the word CAD, computer-aided detection, it really sells it. We don't call things computer-aided anymore. So right from that definition, you can guess that it's been around for a long time. And the work, initial research and development in this area were happening in the 80s and in the 90s. And at that time, they've been developing different approaches to better detect cancer. And what was especially important is to make sure that the radiologists that looked at the images and the results didn't miss those small tumors, didn't miss those small growths that are early stages or could be overlooked. So they've used and applied AI into that use case. What was essentially what is happening is that when the radiologist is scanning and looking at the image result, what they're looking for is the high densities of a tissue. So what's highlighted in red there. And what they want to see if where they are, how many they are, how big they are, how dense they are. So those are some of the things that they're looking at. So before AI was introduced in this field, and it is now approximately 80% of all the scans are done with the CAD, with the CAD method in it. Before, it would take a long time to review those images and make a decision, and it would be there would be a long wait line for this type of task to be done. So obviously what they wanted to do is to speed up the process and help the human to review this information. So this is something today a lot of people are aware of and have seen this use case, and I wanted to bring it to help bridge that, how a simple use case that could be applied in other areas. So when thinking about overall what is AI augmentation is trying to achieve, in a nutshell, it comes to the taking a part of analysis that a human would do and doing it using AI, and then presenting the results to the human so that they can make the judgment call. And the big part of work that isn't talked a lot about is breaking the use case, defining a use case and breaking the problem down to balance it out. Where would AI come in and what would the person do and how they would work together? So from the radiology example that we looked at just now, you would see that how do we detect cancer better is a big problem. And you could look at a lot of data there. You could look at blood work, genetic history. You could look at symptoms that the patient experienced. And you could look at the results of the scan images. And this is where the work goes into which part of that can AI help with and what should we leave to the doctor. So when talking about our use case, so for our specific use case that we apply AI, we were looking at users that have to go through a lot of reports to get pieces and bits of information from them and then make their decisions. So what we thought we should do is to use AI augmentation to pick out and collect those pieces of insight for the user and present it to them so that they can look at it and make their decisions. So essentially AI in this use case is doing all the legwork so that the human can just look at the high-level insights and maybe drill in only into some of them. So how do you break the process? What does it take to simulate the analytical thinking that a human can do? And in finance, it could be a lot of different applications. So I'll try to stay high level, but how do you break it down? So the first step of breaking it down goes into collecting the evidence. You want to look at what do they do today and how do they approach the problem without necessarily replicating everything that they do, because some of that you want to innovate and improve. You want to connect the dots for them or help them to connect the dots, and you want to present them the results so they can look at the output of your augmentation and instinctively make those decisions without feeling like it's more work. So the first part, collecting the evidence, is the it could be easy or it could be difficult. In our case, we were lucky because our AI augmentation project was benefiting from the project that happened before we started, which really took the heavy lifting of collecting internal and external data, bringing on into one place on the infrastructure that is in a state where the memory and processing is powerful, transforming that and cleaning that out, all up, aggregating and defining those metrics and educating the user. So this is where it really comes in. It comes in on top of everything else that has to come together that isn't always up to the data scientist to solve. And sometimes making AI augmentation means starting with some of those early steps and fixing that first. Hopefully a lot of that have already been solved for you or in the process of solving. But from the AI augmentation, the tip of the pyramid perspective, where it really starts is the defining the problem. So one of the things that I've discovered when working with users is that problems don't exist. They don't lie on a shelf somewhere waiting to be solved. They aren't users knowing this is the problem and one day I'm going to solve it. We, every day as decision makers, as analysts, as people that work within a business in a dynamic environment, look at the information and we define what the problem is and then we solve that problem. So the problem isn't there unless it's already defined and it's perceived as a problem and there is an intent to solve it. So this is where it starts, really. Is it the problem? And if it is it worth to be solving? Because we don't solve every problem out there unless there is a benefit to doing so. So when you are looking into the world of the decision maker, and trying to understand from their perspective what are some of the problems that they see, how they define them, how they perceive them. You want to build that into your AI augmentation, because the user and the AI have to exist in the same plane of this is the framework of the decision that is made. So back to the radiology example, we focus on a scan and we focus on the density. This is what they're looking at. This is what they use to make the decision. The world, you narrow it down. But at the same time, you may not want to take everything that they're using to make their decisions. For example, one of the things that they used to not do very commonly is to do a mammogram for young patients, because the problem was perceived as it only happens at a certain age. So today the situation is different, but that was some of the perceptions at the time. So these are some of the biases, or sometimes stereotypes or oversimplification of how the world works that you don't want to build in to your AI algorithm, and you want to avoid. You don't want to reinforce some of their biases when you're designing that. And then it goes to the defining the data. What are the data points that can help us solve the problem? So a lot of this information is working with the users and thinking how some of those tools and techniques that we have in the data science toolbox can be applied to the things that they face in their day-to-day, and how can we improve their day-to-day. The next step is connecting the dots. And this is actually a very interesting part of the process. There are a lot of research on human cognition, perception, a lot of research on how the brain works, and a lot of it is outside of the field of the data science. But if you're interested in AI augmentation, I encourage you to read those articles on psychology, biases, but also biology, how our brain works, how our eyes perceive information, and what do we focus on. Excuse me. So through my work, I've identified 4 different ways that people analyze information, and maybe there are more out there, but those are the ones that I'm seeing. So when we analyze information, we focus on distributions. Where are most of the data points focused on? And sometimes we want to find that cluster of where most of the stuff is. Sometimes we want to actually look at the tail ends and look for what is out there that is not part of the common scenario. People look at relationship. A lot of time you talk to them, they are looking at this in relation to this. They are looking at things that are correlated happening at the same time. So that is an interesting area to focus on and try to simulate with AI. Next one is the composition. So what is the data comprised of? What are some of the things that are included in the data? What are the items? And you may look at things over time and compare different periods to understand the trends. You might look at items and compare the items, compare the data points. So comparison, composition, relationship, and distribution, and those are the ways, the approach that we take to analysis. And there are different, so many different ways to simulate that with AI. Once you've decided that, so going back to our example of radiology, you could look at the distribution. When they're looking at the scan of the breast tissue, they're looking at distribution of the tissue. That's the first step. Then they're looking at density. Okay, so density is important to decision maker. We can measure that. We have data about that. Then they look at the all the data points with high density. So then you can narrow it down. Okay, we're not looking for one particular area. We're looking for multiple areas. So this is how you're breaking down the way that users think into specific areas where you want to solve that with AI. Then you look at what are their judgments criteria, what information do they need absolutely for making that decision, and you build that in as well to make sure that they have that big picture and understanding so they can make their decision. And finally, you present the results. So when presenting the results, because what you have is a lot of data and you need to really narrow it down for the people in a way that's convenient to them, I suggest using an approach what I call a pizza approach. So one slice of pizza might feel great. The second slice of pizza still feel great. But that's the third slice of pizza. So in other words, more information for your decision, still more information for your decision. But when is that point where you feel it's too much information and it's not helping you to make decisions, it just makes you more and more confused. So that approach that you want to build in to make sure that you're not overloading them with information, but you're presenting them with everything they need to make the decision. You can consider ranking it. You can consider building other algorithms on top of that to decide what to present to the user. And you can also think about building in the feedback loop. So putting a little link on the UI saying, was this helpful? Did this make sense to you? And they can say either yes or no. That could also be very useful for ongoing development of your AI augmentation product. So looking at specific problem, let's say we have a digital finance product that is purchased and used by users entirely on their own, so there's no advisor, there's nobody that is needed in the loop, no person to use that product. So there might be a team that is supporting that product, and what they do is they look on a regular basis to see how it's doing, how many people are using it right now, how many people were using it yesterday. And the users might tell you that their use case is that they go in and they see the number of users using the product, and they decide if it's normal or not. And if they think it's not normal, so nobody is using the product, something must be broken, then they go and fix it. So when you analyze this use case, one of the things that you see is that they use comparison. They have a perception of what is a norm, and they compare it to what it is today. Next thing that they do is they compare it over time. They learn what the norm is from what is the overall usage. And then they may have an understanding of what it is, and they have an understanding of what is to expect. So you build your application based on that. So here's an example of what the actual flow could look like. You take the available data, you take the training data for your historical time series. There is a variety of models that you could use for this use case, but let's say you're using the Bayesian space-time series, or you could use LTSM or anything else. Then you look at the historical data, you predict the expected value, and you look at what is the value today. So you have a range of what you thought it could be based on your prediction. And if that value falls within a range, that it's a norm, and you don't do anything. But if the value falls outside of the range, then it's not a norm, and you send a flag to the user. So that's the whole flow of the augmentation. The user then looks at the UI, it looks at the flag and decides if they need to take an action or not. And they can provide you feedback. Thank you for the flag. That was really helpful. We are going to fix it. So that's an example of the application. One of the things that I want to make sure you think about when you select the algorithm, when you decide how you will solve the problem, early on, you need to think about how you're going to explain it. So if you plan, okay, you're going to use the Bayesian space-time model, you also need to think, okay, how am I going to explain it to them? How they're going to know that this flag is legit? How they're going to make the decision that it's not? So the choice of the models, maybe you're working with people who are very advanced in their machine learning, they're far on this journey, they're comfortable with algorithms, and they're good with whatever you choose for them. Or maybe you have a high requirement on that explainability, and we need to know exactly where this value come from, and they want to trace it back. Then you may make a different choice. And it's important to start with it rather than try to do it later when all the work has already been done. It's better to do it in the beginning. So you design for explainability and you build for it right away. This is actually one of the things that is preventing adoption today. People are afraid of things that they don't understand, and sometimes they're worried of what would be my process of making the decision in the future with that AI. Is it going to replace me? Am I going to understand it? Do I have the right skills? So you need to address that at the beginning, and explainability is the great way to address it. Put it simply, explainability is providing them with a clear explanation of what is the data that came in, how you did it, what was the analysis and steps, and why those steps were taken. All of those, the how, the what, the why, are important, not just the how. And then how do you judge if your AI augmentation is a success? One is that they understand why you have used certain data points, but it's also important that they understand why you did not use some of the others. So why and why not? You also want to make sure that they know when the flag is correct and they agree with it. But you also need to teach them on how to recognize that the AI made a mistake and how to work with that. They need to have that level set that it helps you to make the decision, but not everything that it brings to you might be something to act on. And not only they need to know when it's correct, they also need to know of when it's not correct and why those mistakes happened. A lot of time, it's not the problem of calculation, it's not the problem of math, but when you look at why something happened that we don't want to happen, it goes back to some of those biases and preconceived ideas and assumptions that were built into the model. So if they give you that feedback that this wasn't helpful, then you go in and you can review that and look into that. So I wanted to leave you with explainability and make sure that you think about it early and you plan for it in addition to everything else. And that's all I wanted to bring to you today. I think we have a couple of minutes for questions. Thank you so much.
Thank you, Olga. That was really interesting. Like every slide was such a bliss to listen to. So let's get to questions now then. We have a couple. Cool. Starting from Ismail's questions. Is AI augmentation the same as decision intelligence, he asks.
Definitions vary. I would be honest. So augmentation is a wider field, and the augmented intelligence and decision intelligence work hand in hand with it. Decision intelligence does not always include AI.
Okay, then the next question. Could you please explain the difference between an AI model versus a classic machine learning model?
It's a great question, and there's a lot of debate into it. So when you're building AI augmentation, you do use a lot of the machine learning techniques that we call machine learning. Where it comes to AI, what it does is it takes a task that a human is doing, and it runs some of those decisions for the human. So when it comes to that, it typically means that you have multiple, not one, but multiple machine learning algorithms that work together and produce some of those decisions. So decisions on should the flag be raised or not, decisions on how do we present it to the user and in what order. So some of those components that aren't algorithm specific, but more of how the whole system operates together, that's what makes it an AI. And it's definitely not as simple as one machine learning model.
Okay. And Shurit, he says, if you go back to slide 11, when you talk about comparison, do you mean comparing between different algorithms, or do you mean comparing the relationship between variables?
Right. So it's actually, I believe this is slide 11. Yes, this is the comparison, the second. So the second from what Surit has mentioned. It's when people compare the relationship between different data points. So in their own analysis process, when they make decision, what are the data points that they take into account, be it the time series data, be it the categorical data, and how do they use this data in making their decision? So sometimes decision does not involve comparison. You don't. But if it does involve the comparison, then how are they doing that comparison? And then what are some of the data science algorithms and overall what is in the toolbox that we could use to simulate that process and replace some of the things that humans might find difficult and challenging with AI?
Okay, and Adam says, do you have favorite resources for learning more about decision augmentation?
So some of the resources that I mentioned were are listed here. So reading articles and research papers is what I do regularly. Is where probably we all go for some of those. Some of the papers that have been published in 2013 and 2014 are getting discovered today and becoming the hot topics. But what I suggest is thinking about your problem and thinking about how it is being solved today with people, and then looking at some of the algorithms that perhaps were designed for something totally different. How could they be applied to your problem is what I'd like to do. So some of it might come from modeling ecosystem. Some of it might come from modeling fishery. Some of them are economic modeling for economic complexity and how the world economy works. And bringing that to your specific problem may enable you to do things that you are not able to do before. So I think from my experience, learning from variety of learning about the problem in a variety of ways is the best way. Not just looking at AI articles specific to what have already been done by other people.
Okay, and another question. When you're building a model, since it's trained on historical data, models may not work due to future scenarios. And how do you account for that?
Oh, this is a great question and something that I like to work with, because this is a challenging situation. So in my example, when I covered the digital tool, so actually looking at app usage or web usage data and seeing how people are involved, you can use historical data and train it maybe on last 24 hours, if that's how long it takes for things to change, or maybe a month, or maybe 3 months if seasonality is the thing, etc. But for some of those problems, you cannot use historical data, and you have to model it through scenarios, right? If you cannot predict a specific, using historical data, you cannot predict a specific where it would end up in the future, then you have to plan for multiple futures,
right,
and for multiple scenarios where it will be involved, which could come from from hypothesis by people adjusting parameters and working with that.
And next question from Breno. Olga, is there any stage along your augmented pipeline that you take analysts' input into consideration?
It depends on the use case, right? So when I talked about the radiology example, you're looking at in that use case, we present to them all the locations when the density is observed, and then they make the decision. What you could do then is to say they could highlight. So today they could highlight certain areas and rerun based on their input, and then focus on those areas and maybe call a patient to come back for a biopsy, or maybe never contact them again because you didn't find anything abnormal. So the same comes with the decision on a flag, right? One of the things that the very minimum you could do is to ask them to tell you if that prediction was helpful or not. But you could also ask them to tell you if they used it in their analysis or not, and you could feed it back to your pipeline to use it for your future predictions.
Okay, and the last question is about operations side of things. Michael asks, are you able to share what your ML or analytics platforms or tools look like at RBC today? How do different personas and roles interact? For instance, the business analysts versus ML engineers versus data scientists. How do they work together using which tools and platforms?
I can't speak to specific tools that we use, but I can tell you that it's a very wide array of tools. And what you do is, if you join RBCs, you have a choice of a large number of things you could do. If you prefer to use certain tools, more likely that there are lots of people like you at RBC who are already using those tools. And if you want to introduce a new tool that nobody is using today, that's also an option, and I've done that. You onboard a new tool. So I wouldn't say there is a limitation to a specific platform or specific area. I know for a fact that we have more than most people are aware of today in terms of cloud, in terms of open source, and licensed solutions as well.
Okay. And I have a question of my own. Like an average use case, like an augmentation case you want to put into production, how long does it take from start to end? How long does it take to integrate this into the normal flow of your work? And could you speed this up in time? What helped you along the way, if you could speed it up?
Sure. So the answer, it could take decades, right? Like with the radiology example, when they first introduced it, what happened was a lot of radiologists were not happy because now they have to review a lot more than they used to review and say, no, this is okay, no, this is okay, no, this is okay. Too many flags created unhappy radiologists. So, and it took a long time until the newer machine learning methods came around, where we are able to speak with more confidence and we have different ways to approach the problem rather than just measuring the density. So the same comes to finance use cases, right? Some of those things that we are trying to solve with machine learning and AI today might be solvable, but there might be new approaches that coming up that would enable us to do it even better in the future. To give a specific example, so one of the use cases that I was explaining today, where a decision maker has to look at multiple reports and dashboards to make a decision, and we wanted to bring to them some of those data points that would be needed for this specific decision and free their hours of their time. So that implementation is going to take about 9 months from the idea and the first conversation about it to actually have one of the users.
Okay. So thank you very much for this presentation. It was really, really interesting. I hope I get to listen to you more in the future. And before wrapping this up, I'll just let our listeners know they can visit our booths, our partners in the booth section in the left tab, and they can meet them one-on-one, the sponsors, and you can register for some prizes. We have some Amazon cards of $100 each, 2 Amazon cards, so you may want to check them out. So thank you everybody for listening, and thank you specifically Olga for sharing your experiences, and have a good rest of your days.
Thank you.
Thank you.
Bye.
Bye.